The typical slingshot can shoot at 165 feet per second. This is about 50.3 meters per second. The meters per second are the units that we like to deal with. As the marble goes straight up into the air and reaches its maximum height at the peak here, we know that the velocity is 0 meters per second. This is because the marble is reaching this peak height and it's going one direction and then changing direction back down to the ground. We know that if the marble changes from positive velocity to negative velocity, it has to go through 0 meters per second. When the marble hits the ground, that final velocity is also 50.3 meters per second. That's because of the symmetry of this nice curve that we see when the marble goes up and down. This is what we know, but what do we want to find? How high did the marble go? We want to find this distance x. It's interesting to note that when we look at this problem, just this part of the problem, it looks like a drop from rest. We could say that our initial velocity is equal to 0 meters per second, right here. And this tells us this is an at-rest problem. Because the curve is symmetric, we can take this complex idea of the up and down and just focus on the top to the bottom. That would mean that our final velocity is 50.3 meters per second. And we want to find x. Looking at our formulas, we could use v squared equals v naught squared plus 2gx. But since this is an at-rest problem, v naught is 0. V squared, we have 50.3 squared equals 2g, which is 19.6x. 50.3 squared divided by 19.6 gives us x, which I have found to be about 129 meters, with a little bit of rounding. That means that when the slingshot shoots the marble straight up into the air, the maximum height this marble is going to reach, x here, is 129 meters. That's pretty neat because we found that by using at-rest formulas, which are the first type of free fall problems that we did. So let's look at how long the marble would be in the air. We still know that the marble was shot up at 50.3 meters per second. The marble reaches its maximum height, which we just found to be 129 meters, at 0 meters per second, and it hits the ground at 50.3 meters per second. If we want to find the total time the marble is in the air, we can still treat this as an at-rest problem. If we focus on just this half of the curve and find this time by using our at-rest formulas, we can double that time to find the entire time of the curve. So let's say that v naught is still 0 meters per second. We can use our at-rest formulas. V is equal to 50.3 meters per second, and we're looking for t. T will just be this half of the curve. Our regular formula is v equals v naught plus gt, but v naught is 0, v is 50.3, And this equals G, which is 9.8, times T, 50.3, divided by 9.8 will equal T. And I found this to be 5.1 seconds with a little bit of rounding. So that means that the time the marble takes from its maximum height up here to hit the ground down here is 5.1 seconds. Due to the symmetry of the curve, the time it takes to leave the slingshot and reach the maximum height is also 5.1 seconds. So if we double this time, or add those two times together, we should get the total time the marble is in the air, from being released from the slingshot, reaching the maximum height, and hitting the ground. It's 10.2 seconds.